Okay, so in this video we're going to find the subsets of a cyclic group and see if there's any properties that we can see within those subsets of each of these groups. Now each of these groups is addition modulus n, and all of these groups are cyclic. Now for n is greater than 2, that is always the case. And then what we're going to use the system of finding the order of each of the elements, and we're going to use this method here. So each element A, and then we do 0 times A itself, then 2A, 3A, 4A, all the way up to n minus 1A, which is what we've got here. And I've listed all of the groups here. So let's go straight away into this one here. So for 0, it's just a trivial one. Keep adding 0 to 0, you'll always get 0. Now for 1, keep adding 1 to 1. We'll go through the whole set. So 1 plus 1 mod 5 gives us 1, and then 2, then 3, then 4, and then if we add 1 again we get 0 mod 5. So that gives us that, which in turn gives us the whole set, the whole group, sorry, of the original group. So our subgroup here is actually the group. 2, so keep adding 2 onto 2. We get 2, 4, and then 6 mod 5 is 1, and then 3, and then we get to 5, which then gives us 0. So this again is the same as the order of element 1, and it also gives the same subgroup, which is also the group itself. Let's try 3. So keep adding 3. 3 plus 3 is 6, which then gives us 1. Add 3 gives us 4. Add 3 mod 5 gives us 2. And then add 3 mod 5 gives us 0. Obviously adding 0 gives us back to 3. So again, this gives us the group itself. Now in the final element, we'll try 4. So 4, keep adding 4. We go 4, 3, 2, 1 and 0, and that's mod 5. So basically the subgroups, so let's say here subgroups are 0, which is the trivial subgroup, and then we've got 0, 1, 2, 3, 4, which equals the group itself. So that's the subgroups of this one. Okay, let's take these off the board. Now let's try this one. So again, 0, keep adding 0. It's the trivial group, just gives us 0. And then keep adding 1, modulus 8, starting from 1. We know that this is going to take us through the whole set. So that's going to yield all of the elements in the original group. So that equals Z8. Okay, what about 2? So this has even number of elements. So keep adding 2, and we're doing addition modulus 8. So we'll end up with all the even numbers that are in the original group. So that's our subgroup there. And what about 3? Starting with 3, adding 3 modulus 8 will yield 3, 6, 9 mod 8 is 1, and then 4, then 7. 7 plus 3 is 10, which then yields 2, and then 5, and then 8 mod 8 is 0. So that also equals the group itself. Okay. So we know we've got 2 generators already. So I'll just put a G there. There are generators. Let's try number 4. So keep adding 4 mod 8. 4 plus 4 is 8, which gives us 0. And 0 plus 4 is back to 4. So that's a different subgroup now. We've got 0 and 4 with just 2 elements. Now on to 5. Keep adding 5 mod 8. Get 5. 5 plus 5 is 10, which gives 2. And then 7. 7 5 is 12, which yields 4. 4 plus 5 is 9, which yields 1. 1 plus 5 is 6. 6 plus 5 is 11, which yields 3. And then 3 plus 5 is 8, which yields a 0. So again, this equals the group itself. And here we've got another generator. Okay, let's try 6, just 6 and 7 left. So keep adding 6 modulus 8. 6 plus 6 is 12, which gives 4. 4 plus 6 is 10, which gives 2. 2 plus 6 is 8, which yields 0. So that's another subgroup. 2 and 6 here are the same. So let's see if there's any link between those two. And then number 7, the 8th element. So keep adding 7 mod 8. We'll go for 7. 7 plus 7 is 14, which gives 6. And then we go to 5, 4, 3, 2, 1, and then 0, which also equals the group. So this is also a generator. So basically we've got 1, 3, 5 and 7 are generators. Now we'll see here that 1, 3, 5 and 7, these are coprime to 8. So any coprime element of this group here will yield a group, will be a generator of the group. And then we've got here, we've got 2 and 6 are the same. So basically what we can see is that we keep adding 2 and 6, we get to 0, which is the identity element. And also 2 and 6 are the inverses of each other. So basically 2 plus 6 is basically the same as 6 plus 2, which equals 0. And 0 is the identity element. So which two elements compose to form the identity element? We know that these are inverses of each other. So therefore we'll see here that these will also form the same subgroup. So that's one other property that we can see in this group. Also as well, every group contains 0. So 0 is the identity element. Now for every subgroup must still contain the identity element. And the identity element under addition is 0. So we're setting ourselves up for this group now with this information. Okay, so I'm going to write down these subgroups now. So we've got Z8, even integers, 0, 4 and 0. Okay, so now use this information here. Let's look at 0. Well, we know that will always yield 0. That's the identity element. So now for all the other groups, let's see if we can work out what they're going to be. Just by using the properties that we found in the previous part. So which of these elements here are coprime to 9? So coprime to 9, we'll see 1, 2, 4, 5 and 7 and 8. So these are all coprime to 9. So my suggestion is that all of these will generate the group. So all of these are going to generate Z9. So you can check these for yourself and we'll see. 5, 7 and 8. Okay, make sure that looks like a 9 and not an A. Okay, so that's the subgroups we've got so far. So all we're left now is 3 and 6. Well, we know if we do 3 plus 6 and 6 plus 3, these will equal 9. And 9, well, mod 9 is congruent to 0. So therefore that's the identity. So I'm going to say that 3 and 6 are the same subgroup. So let's just see if we can show that. So 3 plus 3 is 6. 6 plus 3 is 9, which then goes to 0. So that's our subgroup here. And then for 6, 6 plus 6 is 12. 12 mod 9 is 3. And 3 plus 6 is also 9, which yields 0. So then we can see that these two are in fact the same subset. So let's just write that down now. The 3 subsets is all we've got here: 0, 0, 3, 6, and then the group itself. Okay. So we've got 0, 0, 3 and 6, and then Z9 itself. Okay, let's see what properties we've got. So basically, each element of each of these subgroups must be in the group itself. So we can see here that all those properties are all ticked. So let's put subgroup axioms here. So 1, all elements in S, and we'll call that Sn, so subgroup of 5, 8 and n. So for here we call this one maybe subgroup 5, subgroup 8, and this one here subgroup 9. So we just call it an Sn. Is also in the main group, so basically he's in Zn. Okay, number 2, are they commutative? So is, for example, 2 elements A and B the same as B composed with A in the subgroup? Well, we know composing all of these in 5, in Z5, will be commutative. So 1 plus 3 is 4, which is in it. And then if you do 4 plus 2 is 6, mod 5 is 1, which is also in the group. So the commutative rule works for this one. Let's try this group. So 4, 4 and 0. 4 plus 0 is 4, and 0 plus 4 is also 4. 2 plus 4 is 6. 6 plus 2 is 8, which yields 0. So yes, that's commutative rule works for these subgroups in S8. What about 9? So we know all of these are going to be commutative. What about 0, 3 and 6? Well, 3 and 6 is 9, 0 and 3 is 3, 0 and 6 is 6. So the commutative rule works in the subgroup axioms for all of these groups. Then what about 3? Identity. So the identity element in these groups is 0. And we can see that 0 is in all of these groups. So the identity element in Zn must be in Sn. Okay, and then what about the fourth one is inverse. I'll put inverses. Now each subgroup must contain its own inverse. So the inverse of 3, 3 plus 3, 3 composed with 3 is 6. The inverse of 6 will give us 3 in this group. And it'll be the same for all of these groups. So therefore we can say that all these subgroups here tick the subgroup axioms. Okay.